All right, let's get started. So today's lecture is going to be a little bit of a change of pace. We're going to talk about variational inference and generative models, which doesn't directly tie into DeepRL, but it's something that we're actually going to build on in some subsequent lectures on exploration and on modeling human behavior. But first, a few class notes. So homework 3 is due next Wednesday for real this time. So please do make sure that you're well on your way to finishing homework 3. It does take quite a bit longer to run than the previous homeworks. If you take a look at Piazza, you might notice some people asking questions about why it's taking so long and how long it really takes. So that should be a clue to start on it early to make sure you don't run out of time waiting for your experiments to complete. Second point. By this time, everyone should have really accepted the CMT peer review invitations. If you haven't yet, if you are not a reviewer in CMT for the project proposals, you need to get this fixed immediately. So this is required. It's part of your final project grade. If you are not currently a reviewer on CMT, contact Kate Rakelli right away. So you can find our contact information on the course website, and you should get that taken care of today because we're going to need to complete those peer reviews soon. To get feedback to everybody about their project proposals. And then the TA feedback about the project proposals will be out shortly. Okay, so where are we in the class so far? We're actually right now right at the halfway point. We're here in lecture 14, which is halfway through the class. The first half of the class was really focused on reinforcement learning algorithms. And as of last Wednesday, we finished that portion of the class, and we've given you guys the overview of the important reinforcement learning algorithms that we're going to teach you. The second half of the course is concerned with advanced topics. These advanced topics will include inverse reinforcement learning, inferring reward functions from demonstrations, exploration, a connection between probabilistic inference and control, transfer learning, meta-learning, parallelism, system design, and then advanced visitor lectures from Craig Boutillier, Kwok Lei, Carol Hausman, and also a few of the course TAs who will talk about their research. So the purpose of the second half of the course is to give you a broad overview of advanced topics in reinforcement learning and also some state-of-the-art research topics. So we'll have research talks about cutting-edge work to get you guys some ideas that maybe you might want to incorporate into your final projects. But for today, we're right here. We're on lecture 14. We're already finished with the overview of reinforcement learning algorithms, and lecture 14 is going to help build up the foundations that we'll use later on for some of this advanced stuff. So today's lecture is actually not going to be about reinforcement learning algorithms, although we'll see towards the end there's some funny ways in which reinforcement learning can actually be useful for probabilistic inference, maybe in ways that you don't expect. But primarily the purpose of today's lecture is to build up a foundation in probabilistic inference and probabilistic models that will be useful for us later on. So what's today's lecture about? Today's lecture is about probabilistic latent variable models. So we're going to introduce probabilistic latent variable models. Many of you probably already know about the basic idea from your machine learning class. We're going to talk about variational inference, which many of you might have covered in your machine learning class, but if you haven't, then this will be an introduction. If you have, then it'll be a refresher. But after that, I'm going to talk about something called amortized variational inference, which chances are would not have been covered in an introductory machine learning class, but is actually very important in deep learning. So in deep learning, when someone says, I'm using variational inference, almost certainly they mean amortized variational inference. And we'll learn about what that means. Then we'll talk about a particular very popular class of generative models based on amortized variational inference, which is the variational autoencoder. And I'll conclude with a few examples of how these things can fit into RL, but the kind of really advanced applications will come later in subsequent lectures. So the goals for today's lecture will be to understand latent variable models in deep learning, understand how to use amortized variational inference, and then familiarize yourself with some standard classes of models that use this, like variational autoencoders. All right, so probabilistic models. This is sort of the refresher from your machine learning class. The simplest probabilistic model you can think of is a model that estimates P of X. So just to make this concrete, maybe X consists of vectors in 2D, and you're going to choose a class of distributions that you want to fit to P of x, maybe a Gaussian distribution, so that just amounts to estimating the mean and variance of those points. Very straightforward kind of thing. The second simplest kind of probabilistic model, and the one that maybe we're more often concerned with in this class, is a conditional model, P of y given x. And of course, this is from introductory statistics. If you're doing regression, that's a conditional model. Y is the vertical axis, x is the horizontal axis. But in the world of reinforcement learning, we've already seen conditional models in the form of policies. So the policies that we spend so much time talking about, they're, of course, conditional probabilistic models. They give you a distribution over A, condition on S. So hopefully everyone's all good with that. But today we're going to talk about a particular class of probabilistic models, both this type and this type, both conditional and not conditional, that have latent variables. So what are latent variables and why should we care about them? Well, let's say that you want to learn P of x, but now you don't have data that's distributed in some really convenient way like a Gaussian. Maybe it's distributed like this. So you look at this picture, the color coding is just for your visualization, and obviously you'll think that this consists of 3 separate clusters. So what that means is that there's some kind of underlying structure to the data besides just x that's going to help you model it. In this case, that structure is which of these 3 discrete clusters the point belongs to. So a very convenient way to write down a model to represent this type of data is to introduce an additional variable that is not directly observed from the data that we're going to call z. And in this case, z corresponds to the identity of the mixture element that the data comes from. So maybe you want to model this with 3 Gaussian clusters, which is a very convenient way to model such data. So then you can express P of x as the sum over all possible values of z, which here is categorical with 3 values, of P of x given z times P of z. Okay, so this is the, for example, mixture of Gaussians model that probably all of you saw in your machine learning class. And z here is the mixture element. You can do exactly the same thing with conditional models, of course. So if you have P of y given x, you can, in exactly the same way, write it down as a sum over z of P of y given x comma z times P of z. So in the same way that you can have a mixture of Gaussians, you can have a conditional mixture of Gaussians, where the output is dependent on z. And the z itself can also depend on x. So this could be P of z, or it can be P of z given x, if you like. And we saw these types of models actually before, quite a long time ago in the beginning of the course, when we talked about imitation learning. So those of you that remember, we had this example in imitation learning where sometimes you have a multimodal policy. So if you have a person demonstrating how to drive a car and they drove around the tree to the left sometimes and sometimes to the right, if you try to fit this distribution with a unimodal policy, then over here in the beginning you're in for a bad time because you'll average these 2 modes and hit the tree. But if you can represent a multimodal conditional distribution, it's a policy, so it's a conditional distribution. If you can represent a multimodal conditional distribution, then you can figure out that this data has 2 modes, one that goes left and one that goes right, and does not assign a lot of probability mass to going in the middle. So we saw a few different models that work like this, but maybe one of the simplest was the mixture density network. So this is from like lecture 2 in the course. We had mixture density networks, which are neural networks that look at the observation and then output the parameters of a mixture of Gaussians, which are actually the parameters of P of y given x comma z, and in this case P of z given x, because the mixture weights w are actually also dependent on the image. So you can have conditional latent variable models. And the latent variable, again, is the identity of the mixture element, because the data doesn't tell you which mixture element is being used for which data point. So these kinds of latent variable models, the latent variable models where the latent variable is discrete and takes on a very small number of values, are very easy to deal with, because you can write out the sum, you can implement that sum in a computer, you can use your favorite automatic differentiation software, there's no problem. So if it's a sum over a small discrete set, you can write it down and go with that. You might still choose not to do it that way. So if you're doing clustering, many of you probably learned about EM clustering, which doesn't actually directly write down the sum, but has a more clever way of doing it. But writing down the sum directly is fine. And certainly for mixture density networks, it works just fine. But sometimes using a latent variable that takes on one of a small discrete set of values is not quite good enough. So let's say that I'd like to represent a really, really complicated distribution, some crazy wavy thing that is not easy to approximate with a small discrete number of mixture elements. Perhaps if I'm being a little more clever, what I might say is the following, that, well, whatever this distribution is, whatever kind of complicated, messy thing it is, it's some function of a random number. So I can generate a random number, let's say between 0 and 1. I can transform it with some nonlinear function, like the CDF, the distribution, and I can basically represent any distribution I want. And that makes sense. Like if you're implementing in a computer, how do you sample from the distribution? Where you're going to generate a random number, and then you're going to transform that random number. So that means that pretty much for any distribution that you can think of, you can represent it as some nonlinear transformation of a simple distribution. And which simple distribution we want to think of, that's kind of up to us. A very popular choice is to use a Gaussian distribution because everything is easier and more fun with Gaussians. So you can imagine taking a sample from an easy distribution like a Gaussian distribution, transforming it with some complicated nonlinear function, and getting a sample from any distribution you want. And now we know that neural networks, deep neural networks, can be universal function approximators, meaning that for any function that you would care to approximate, you can build a big enough neural network such that it will approximate that function to arbitrary precision. So if we want to figure out how to transform this easy distribution into the one we care about, well, we can use a big enough neural network. So for example, we could say our P of z is going to be Gaussian because Gaussians are easy to deal with. And then we're going to transform samples from this Gaussian into samples from our complicated distribution by using a simple distribution whose parameters are a complicated function of z. So we'll say maybe P of x given z is also something easy like a Gaussian, but the mean and variance of that Gaussian is a complicated arbitrary nonlinear function of z, which we could represent with a neural network. So this type of approach can actually model any distribution because the neural networks are universal function approximators, provided you make your network big enough and with all the usual caveats about optimizability and so on. So it's quite desirable for us to be able to deal with latent variable models whose latent variables are continuous, because then we can convert them into whatever we want. But there's some bad news here, because now that sum that used to be a sum over a small discrete set is now an integral over a continuous variable. The good part is that it's an integral of a product of two terms, and both of those two terms are actually easy. So P of z is some easy distribution like a Gaussian. In fact, oftentimes in practice, we won't even learn that distribution. We'll just fix it to be a Gaussian with mean 0 and variance 1, because we don't care. We're going to be transforming it with some arbitrarily complex nonlinear thing. P of x given z is also easy in the sense that it's some simple distribution like a Gaussian whose parameters, mean and variance, are given by a neural network. So even though the product of the two might have a really complicated shape, each individual part is relatively simple. The challenge with these models comes from the fact that it's this integral. So you have to integrate out z, and of course z is continuous, so approximating this integral is quite hard. Does anyone have any questions about this type of latent variable model? Yes?
So why do not you sample from the Gaussian and let the neural network take the inputs of this Gaussian?
Mm-hmm.
You just instead to calculate the mean and variance of z.
Right. So let me try to understand your question. So this this distribution is Gaussian condition on z. This distribution is Gaussian, period.
Yeah.
But when you take the product of these two and you integrate out z, the result is not necessarily Gaussian. Because each of the point, basically, the intuition is that each point that you sample here is transformed into something up here via nonlinear transformation. So these neural networks can choose to take a point here and put them in the same place, for example, and or put like 2 points that are close together very far apart in the output.
I mean, another way is that your neural network can take the input of PZ input of Z. That means you give a Z, then Z goes to a neural network, then the output.
Yes.
Here it is different because it's just calculating the mean and the variance and then sample from that Gaussian.
So let me try to clarify this picture a little bit. So this is your target distribution. This is your P of x. This is your source distribution. This is P of z. What P of x given z does is it takes a point over here and it maps it to some distribution over here. This thing that it maps to is Gaussian. But once you integrate out z, that basically amounts to summing together an infinitely large number of Gaussians. And because there are infinitely many of these things, they can actually approximate any target distribution. So the key is that z is being integrated out. You can think of it as essentially as a mixture of Gaussians with infinitely many mixture elements. All right. So let's go through a few examples of where we've seen latent variable models crop up in reinforcement learning. And in fact, we've actually seen latent variable models of this type crop up in a few places, and we'll see them a lot more later. So we saw this example when I talked about the multimodal imitation learning. So I talked about a few different classes of policies we might use if we want to represent multimodal conditional distributions, including mixture density networks. Yes?
To be clear, we haven't talked about the computational mechanism for doing this integration, right? We've just
No.
written down the form.
Yeah, so the rest of today's lecture is about the computational mechanism for actually doing this, yeah. Before I tell you about how to do it, I want to tell you why to do it. Otherwise, some of you might be tempted to walk out of the room and not listen to the rest of this. So I want to explain why we should care about this, and then the how. One of the reasons why is that if we want to do imitation learning and we'd like to learn a multimodal policy, you can learn a multimodal policy with policy gradient too if you like. There are a few ways to represent multimodal policies. One of them was mixture density networks. But if we want to represent arbitrary multimodal distributions, one of the things we covered in the beginning of the course was models of this type, where you generate some noise from, let's say, a Gaussian distribution with mean 0 and variance 1. You feed that noise as input into your neural net in addition to the image, and then you have that output, your output distribution. Now, training these types of things so that they actually use the noise properly is a little tricky, and the methods that we're going to discuss today can actually allow us to do that. But if you can train these models appropriately, then they can use this noise to output any distribution you would care to get. So in the parlance of latent variable models, this noise is P of z, and this mapping is P of y given x comma z. We've also seen models of this type when we discussed model-based reinforcement learning with images. So if you remember this picture, where we're taking observations and we're embedding them in some latent space so that we can then do control in that space, that is a latent variable model where the observed variables are O and the latent variables are X. And pardon the confusion in notation because now X is latent, whereas here X was observed. So it's just a notational change. So here, the latent variable model is O given X, and there is a prior on X. And in fact, if you're dealing with a sequential process, X itself might have some kind of structure on it. So perhaps you actually don't want to model all the X's as being independent. Maybe you also want to model relationships between the X's, which is what you would do if you want to learn dynamics in the latent space. So that's what was happening actually with those embedding models when we talked about advanced model-based RL. So the latent space here has structure. Okay, so these are a couple of places where we've seen these models already. We'll see a lot more of them going forward. We'll see some examples of variational inference and latent variable models when we talk about using principles from RL and control to analyze human behavior. So you can actually, if you assume that a person is acting in some near optimal way, you can observe their behavior, model it as though they were solving a control problem, and perhaps you can figure out what their objective is, what they're trying to accomplish. You could also use generative models, including latent variable models, for exploration. So in exploration, we'll see that these models can be very useful for trying to determine whether a particular state you're seeing is a new state that you've never seen before, or a state that you've visited many times. And that can be used to guide exploration, to encourage your policy to visit new states. So we'll see a lot more about both of these ideas in the coming weeks. So in order to get there, we need to know how to actually train these latent variable models, how to deal with this horrible integration issue. So let's work with the simplest type of model for now, and we'll actually come back to conditional models at the end of the lecture. So the model we'll work with for now is just P of x. And I'm going to write it as P subscript theta of x to make it clear that this model has some parameters. How do we train this model? Well, we need some data. So our data consists of examples, x1 through xn, and we'll do what we always do, which is maximum likelihood. So if you have some data, you want to train some model, maximum likelihood. Maximum likelihood just means you're going to choose theta that is the argmax with respect to theta of the sum of the log probabilities of all your data points. That's pretty straightforward. So maximum likelihood is what we use to fit our data. But of course, the trouble is going to occur because of the form of our model. So P of x, of course, is this intractable integral. So if we substitute that in there, we have log of an integral over all possible values of z of P theta xi given z times P of z, which is pretty awful. For simplicity, I'm going to assume that P of z doesn't depend on theta. You can have P of z depend on theta also, but oftentimes you leave P of z fixed because you can transform any distribution to any other one with a nonlinear function, provided that it has full support. So just a Gaussian here is perfectly fine. A Gaussian with mean 0 and variance 1. But it's straightforward to generalize this to the case where you learn the prior if you would like to. Okay, so this integral is intractable, and that's what we're going to deal with. So what can we do? Well, here's an alternative. I'm not really going to justify this alternative because I'm going to justify a much more general case later, but intuitively this alternative kind of makes sense. Maybe if you don't know what the value of z is for each of your data points, maybe you can guess. So perhaps what you can do is, for each of your data points, figure out what's the probability of z given the data point x, and compute the expected log likelihood, the expectation of the log likelihood under your guess about what z might be. So the intuition, you guess the most likely z given xi, and you kind of pretend it's the right one. But in general, you might not be sure about what the z is, so instead of just picking one z, you have many possible values, so you use the whole distribution z given x. It kind of seems like a reasonable thing to do. If you're not sure which cluster a particular data point is, guess the cluster and then maximize its likelihood under that cluster. And if it falls between two clusters, then maximize its likelihood under both, weighted by 0.5, for example. So that's a very reasonable thing to do. It's called the expected log likelihood, and that's what's used in expectation maximization. But when we have these complicated latent variable models, when z is continuous, this kind of approach doesn't really help us either, because now we're faced with this other problem of calculating z given x. So when we have discrete z's and we have clusters and so on, z given x might be straightforward to compute. But when we have this kind of situation where we're transforming a continuous variable into a probability of another continuous variable, z given x might be extremely complicated. Because if you look at a location over here, it might have come from many different places over here. In fact, it might have come from multiple places, because this forward mapping, x given z, might take some mass over here and some mass over here and put both of these in the same place. It's allowed to do that. So in general, z given x might be a really complicated monstrosity, and not only is it difficult to calculate, it's difficult to even represent, because it might be an arbitrarily complex distribution. So what if instead of calculating z given x, we just approximate it with some simple distribution? We say, okay, z given x is going to be a mess, but maybe it's good enough if I approximate it with something simple, like a Gaussian. Some distribution that I can tractably parameterize. And we're going to call this distribution qi, because this is a guess at the distribution over z given xi. So it's not a q of z for everything, it's a q of z specifically for data point I. So for data point I, we'll have some parameters mu I and some parameters sigma I that define, let's say, a Gaussian. It doesn't have to be a Gaussian, it can be any analytically parameterized distribution, but we'll go with Gaussian for now because it's easy for us to deal with. It turns out that if you set up your objective in the right way, you can actually use this qi of z to bound the quantity that you want, which is log p of xi. You can't compute log p of xi exactly, because of course this qi of z is not exactly p of z given xi, but you can construct a lower bound on it, which means that if you maximize that lower bound, you will also push up the entire log likelihood. And this is called variational inference. So here's how it's going to work. It's actually a very simple technique. First, you write down the log likelihood that you want, which has this intractable integral in it. And then you're going to multiply it by 1. Multiply something by 1 doesn't change the quantity, but it turns out, very convenient for us, 1 is equal to qi of z divided by qi of z. Nice identity, true for any number, but we're going to opt for qi of z. So multiplying by 1 is always a fun thing to do when you're doing some kind of mathematical derivation. And now you can actually take this thing and you can write it as an expectation under qi. So you take that qi at the top and you make that into an expectation, just by definition of expectation. And you have an expectation under z distributed according to qi of the ratio between your model, p of x given z times p of z, and q of z. Now, you're still in trouble because this expectation involves an intractable integral. And the next part is the one where we're going to turn this equality into a bound. So to turn into a bound, we're going to use a very useful identity called Jensen's inequality. And Jensen's inequality states that if you have the logarithm of an expectation of something, that is always going to be greater than or equal to the expectation of the logarithm. As a quick practical tip, if you're using Jensen's inequality in a derivation, make sure you get your signs right. So this thing is positive and you want to maximize it, so this thing on the right is going to be a lower bound on this. If it was negative, you need to flip the inequality. Very common mistake. But for now, we're okay, because we're maximizing log e of y. So if we instead maximize e of log of y, that's going to be underneath it, so it'll always push it up. So we're going to apply Jensen's inequality, which means we're going to take the log and put it inside the expectation. So this thing over here is greater than or equal to the expectation of the log. And now we're in business, because when you have the logarithm of a product of a bunch of terms, logarithm of a product is sum of logarithms, so we're going to be able to simplify this tremendously. So we're going to expand this out by writing it as a sum of logarithms. So you have the expectation under qi of the log of the numerator minus the expectation of the log of the denominator. So we basically took all three of the terms in this ratio and we wrote it out as a sum. Now there are a few interesting things that happen here. The first interesting thing, which I'll discuss a little bit, is that this last term, the one that doesn't depend on p, is simply the entropy of q. So all I did is I replaced the last term with this funny script h. What is entropy, and why do we care that term is equal to entropy? Let's talk about that a little bit. So, but first, a quick comment just to explain where we're at. Because this thing is a lower bound on log p of x, we know that if we can maximize this thing, it'll push up log p of x. So this is the thing that we need to maximize. We're good on that. Now let's understand why this entropy is there and what it means. So as a brief aside, many of you might already be familiar with differential entropy, but entropy is basically defined by this equation. So the entropy of some distribution p is the expectation under p of the log of p, and then you put a negative sign out front. So what is this thing? You can draw it. You can take, let's say, a Bernoulli random variable and plot the entropy as a function of the single parameter of a Bernoulli random variable, and you'll see that entropy goes up as the probability of the binary variable approaches 0.5, and it goes down to 0 on the tails. That kind of makes sense. Deterministic variables have an entropy of 0. Very, very random variables have high entropy. So the intuition behind entropy is that it measures how random a random variable really is. Deterministic random variables have the least entropy. Very stochastic ones have the most entropy. But also looking at the equation, it's kind of intuitive what it's doing, because it's essentially measuring how large is the log probability in expectation under itself. So if the distribution has low log probability under itself, that means it assigns low probabilities to the things that it's likely to pick, which means that it must be very random, because distributions have to sum up to 1. So if you have a continuous random variable and your distribution looks like this versus like this, that one will have high entropy and this one will have low entropy. So it's kind of how wide is the distribution if we're talking about continuous random variables. So now in light of this intuition, let's go back to our bound and let's analyze what it's doing a little bit more. So our bound consists of two terms. It has one term for entropy, and we're maximizing this, so we're trying to make entropy big. And it has another term for the expectation of this thing. And this thing here, just by the chain rule, you can see that this is actually the log probability of xi comma z, right? So if we just had that first term, the expectation under q of z of log of p xi comma z, what we would do is we would find the z with the largest probability, right? So we would pick the mode of our target distribution. That kind of makes sense. Finding the most likely z seems like a useful thing. But because we're also maximizing the entropy, we're going to try to find that mode and then have q of z be as wide as possible. And if you try to find the mode and then make your distribution as wide as possible, you're essentially going to cover all the probability mass that sits at that mode. So you're going to try to get closer to your target distribution, not just in terms of the peak, but also in terms of the width. And we can actually make this intuition a little bit more precise. We can make it a little bit more precise by introducing something called KL divergence. And I've mentioned this term before, but I want to provide a little bit more intuition for it now, because it's going to be really important for what comes next. So KL divergence, if you look it up in a textbook, has a very simple definition. It's a function of two distributions, and it's the expectation under the first distribution of the log of the ratio between the two distributions. And we can also write it like this, because you know that the log of a ratio is the difference of the log, so you can also write it as the difference between the expectation under q of log of q and the expectation under q of log of p. Which, of course, is the negative expectation of log of p minus the entropy, because this term here is just the negative entropy. So KL divergence measures how different two distributions are. If the two distributions are exactly identical, then it's easy to see from this middle equation that KL divergence would be 0, because if q is equal to p, then this is log q, so you take the difference, you get 0. And KL divergence increases as the distributions become more different from each other. And then the other intuition is that, well, it's how small is the expected log probability of one distribution under the other minus its entropy. And that minus entropy is what makes you actually match the whole distribution. So just like before, we saw that if we just have a term like this, so let's say we're minimizing, so that means that we're maximizing the positive one, we pick a mode. But if we also try to maximize entropy, then we try to make that as wide as possible, which tries to match more of the distribution. So the entropy term is what makes you not go from picking a mode to actually matching the whole distribution as closely as you can. All right, so now let's actually use this KL divergence to analyze that bound a little bit more to understand a little more closely what it's doing. So this is the bound that we derived. We derived that the log of the probability of xi is lower bounded by the expectation under q of z of log p of xi given z plus log p of z, which is just log p of xi comma z, plus the entropy. Yes, question?
Can you explain again why maximizing the first term gives us the mode?
Yes. So it's perhaps easiest to understand from this picture. So maximizing the first term is the same as minimizing this thing, right? Minimizing the negative, maximizing the positive. And what is this? This is the expectation under q of the log probability. So the best solution is to put all of your probability mass onto the value with the largest log probability. Because if there's a particular point in your target distribution, so this is p of x, and this is x, so there's a particular point that is a maximum. Any probability mass that you put on any other point, like here, this will have a lower log p than this. So you want to put all your mass on the very top. So if it wasn't for that entropy term, the best solution for q of x here would be the lowest entropy distribution, just a Dirac delta, with all the mass right there at the peak. So in fact, I drew it incorrectly here. It should be just a straight vertical spike. But the entropy then makes it as wide as possible. Okay, so let's work a little bit more on this bound and try to understand what this bound is doing, and also understand a little bit about what kind of q should we use, how should we pick the q. So the bound is valid for any Q. But of course, for some Qs, this bound will be much better than for others. So for notational convenience, I'm going to refer to this quantity as script L. Script L subscript I because it depends on I. And this is sometimes called the evidence lower bound or the variational lower bound. So if you see someone say evidence lower bound, they mean this thing. Okay, so what makes a good Qi of Z? Well, the intuition is that Qi of Z should approximate P of Z given Xi. The intuition kind of makes sense because we had this expected log likelihood before and so on. But we'll actually derive why this is not just intuition, it's actually a mathematical truth. So in what sense should we approximate it? Well, we've just learned about this Kale divergence thing, so let's try Kale divergence. It seems like maybe worth a shot. So what if we try to approximate by minimizing a Kale divergence of this sort? The Kale divergence between Qi of Z and P of Z given Xi. Why? Well, let's write out the Kale divergence. Let's see what it actually comes out to equal. So the definition of Kale divergence is just the expectation under the first distribution of the log of the ratio of the two distributions. And then what we can do is we can take this conditional here and we can apply the definition of a conditional distribution to turn it into a ratio where on the bottom we have xi comma z and on the top we have p of xi. Because you know that p of z given x is equal to p of x comma z divided by p of x. That's just the definition of conditional distribution. So we can substitute that in there and get something like this. We want to do that because we want to express this in terms of terms that we know. We don't know z given x, but we know this thing and we know this thing. So now we can do the usual thing, write out the log of a big product as a sum of logs. So we have the denominator here, which I've expanded out because xi comma z, p of xi comma z is p of xi given z times p of z, so I can expand it like this. This is the first part of the numerator, the q, and this is the second part of the numerator, the p. And now we can see that this part is the entropy, and this part, the interesting thing here is it's an expectation under z of log p of x. But log p of x doesn't depend on z, so you can just eliminate that expectation. So the second term turns into entropy, and the third term just turns into your likelihood. And now you can notice that these first two terms together are precisely equal to the negative of our evidence lower bound. So we can take our evidence lower bound and we can substitute that in there. So now something pretty interesting happened. We see that this Kale divergence is the negative of the evidence lower bound plus the likelihood, which is the thing that we actually want. Which means that the likelihood, if we just shift this negative L to the left, on the left side of the equality, the likelihood is just the Kale divergence plus the evidence lower bound. And we know that Kale divergence is always positive because it measures the difference between two distributions. They can't be any more similar than 0. So because this term is always positive, this is actually another way to derive the bound, because a positive number plus L has to lower bound, L has to lower bound the likelihood. So we have this, bound, but now we can also see that the closer Qi of x, sorry, this should be Qi of z, this is a typo. The closer Qi of z comes to P of z given x, the tighter this bound becomes. Because if the Kale divergence is 0, this inequality turns into equality. So the right choice of Qi is to bring it as close as possible to P of z given xi. And the closer it is, the tighter the bound becomes. Question?
Was there any reason that you chose the Kale divergence of Q given P, like not the other way?
Yeah, the reason I chose this Kale divergence is because if you go the other way, this nice result doesn't come out.
Is there any intuition behind that?
Yes, there is. It'll take a little while to get into that, but I'd be happy to answer that question maybe during the break or something. Yeah, there's a little bit of intuition. But the algebraic reason is that it doesn't work if you don't do that. Okay, so now let's actually use this thing. Like we've derived something, we kind of know what we want. Let's make use of it. So making use of it means we need to get an objective that we can actually use to optimize P and to optimize Q. So we know that our likelihood is equal to this, which means that we want to make L big, we want to make DKL small, and we know that making L big with respect to P is going to push up the likelihood, and Q needs to be chosen so as to make this first term small. However, it turns out that making the Kale divergence small with respect to Q is actually equivalent to maximizing the evidence lower bound with respect to Q. And we can see that if we go back to our definition of the scale divergence, so this is exactly the derivation on the previous slide. I write out the definition of conditional distribution. I expand the log. Now this is the scale divergence. This last term doesn't depend on Q at all. It only depends on P. The first two terms are the negative evidence lower bound. So if we want to minimize the scale divergence with respect to Q, all we have to do is minimize these first two terms, which means maximize the evidence lower bound. So in order to train P, we maximize the evidence lower bound. In order to train Q, we maximize the same evidence lower bound because it's equal to the scale divergence up to a term that doesn't depend on Q. Okay, so that means that maximizing L is all we need to do. We just need to maximize it with respect to everything. So now how do we do this? How do we do the maximization? So we wanted to do the argmax of the log likelihood, but instead we're doing the argmax of the evidence lower bound. And here's how we can do it. We're doing deep learning, so we want to do stochastic gradient descent, probably with mini batches. I'm going to derive it for the case where the mini batch is size 1, but the extension to larger mini batches is very straightforward. You just average over multiple data points. So if you want to do stochastic gradient descent, you sample your mini batch, then you calculate the gradient of the evidence lower bound with respect to theta, with respect to the parameters of your P. So how do you calculate that gradient? Well, you sample a z from qi of xi, qi of z, this is a typo, should be qi of z. And then you estimate the gradient of the evidence lower bound by estimating this expectation using that sample of z, right? If you have an expectation, you want to estimate that expectation, you can use samples. These samples from what? Samples from q of z, which is exactly what these are. And then the only term inside that expectation that depends on theta is the first one. So you just have to calculate the gradient with respect to theta of log p theta of xi given the z that you just sampled. And this gives you an unbiased estimate of the gradient with respect to theta. And then you do gradient descent, or atom, or whatever you want. That's pretty straightforward. Training the theta is straightforward. But you also have to update all of your QIs. You have to update your QIs so as to maximize the same evidence lower bound. So then you might ask, well, how do you update the QIs? Well, let's say that your QI is given by a Gaussian with some mean mu I and some variance sigma I. You could just compute the gradient of your evidence lower bound with respect to mu I and with respect to sigma I, and then try to climb that gradient. And that'll actually work. So you're just doing gradient ascent on theta and gradient ascent on the parameters of your variational distribution. Up until now, this is basically the textbook derivation for variational inference. But here's the issue. The problem with this procedure, well, first of all, I should say this procedure will work. But the problem with it is the following, that if you're doing deep learning, your p theta is some big neural net, your q's are these Gaussians, and your data points are very, very numerous. If you're doing deep learning, you better have a lot of data points. So how many parameters are there total? Well, you have the number of parameters in theta, that's your deep net, and then for every single data point, you have the number of parameters in mu and the number of parameters in sigma. So the total number of parameters that you're fitting when you're using this procedure increases as the number of data points increases, which is not a problem if you have like 100 data points, but if you have millions of data points, you might have a lot more parameters over here than you have in your entire model. That can be a problem. So what we're going to do, and we're going to derive this after the break, is we're going to actually modify this qi of z so that it still approximates p of z given xi, but the number of parameters doesn't scale with the number of data points. How are we going to do that? Well, we're going to do what we always do in deep learning, which is we're going to train a neural net. So instead of explicitly representing mu I and sigma I, we'll actually train a neural network such that qi of z is equal to q of z given xi, which is given by some neural net. And then we're going to try to get this q of z given xi to be approximately similar to p of z given xi in terms of scale divergence. So all we've done is we said, instead of trying to explicitly keep track of the mu and sigma for each data point, just learn a neural net that gives you that mu and sigma as a function of xi. So that means that we have one neural net that goes from z to P of x given z, and we have a second neural net that goes from x to Q of z given x, and we're going to call it Q subscript phi to emphasize that it has parameters phi. So now we're going to take a 3-minute break, and after the break, I'll explain how to actually train this inference network. So we'll be back at 10:56.
What exactly happens if you have actually 2 peaks?
I guess?
Yeah, of the same height. Which one it will pick? Or will it average it? And
You mean if you minimize KL divergence?
yeah.
So this is actually where it matters which way the KL divergence goes. So if I want to minimize a KL divergence of this form, then what I'll actually get is I will get a lot of mass on one peak, and I might miss one of the peaks. So it'll look something like this. And the intuition for this is the following. Let's draw a different picture. Let's draw a picture where the peaks are very disjoint, and over here the probability goes to 0, right? The KL divergence is the expectation under Q of log of P minus the entropy. So if P is 0, log of P is negative infinity. So if Q puts any mass over here at all, if it's like this, it gets negative infinity cost for this. So it's going to avoid this low point at all costs, which means that it'll pick only one of the modes. If you make the KL divergence go the other way, if you have it be P to Q, then you'll actually get the opposite behavior. You'll actually get moment matching. So there Q will try to cover all the peaks, even if it means falling in the gap between them. So the one that we use in variational inference looks like this. The one that, if we go the other way, looks like this. And the second one is sometimes referred to as moment matching, because the moments of this distribution will match the moments of the target distribution.
And if the 2 peaks are of exactly the same height, it will be just random, one of them?
Then both solutions have equal KL divergence.
Yeah, but what if one has one is bigger than the other? Then the option that enlarges them.
Right.
Is like
Yeah, it depends. It depends on how big and how wide.
Okay. Small question. So I told you that it takes a long time to run the Q learning. Do you think it's okay to start running the replay buffer, like inserting from the beginning some samples from the expert and like
That can certainly make Q learning faster, yeah. So if you want to read up on methods that do this sort of thing, look up an algorithm called DQFD, which essentially does exactly what you just mentioned.
Do you still have time, or?
No, I should get started, but maybe after the lecture. All right, we're going to resume. So before the break, we left things off on a cliffhanger where we talked about how maybe instead of keeping separate variational parameters for every single data point, perhaps we can do the deep learning thing and just train a neural network to give us the mu and sigma for z as a function of xi. So now we're going to have a second network, q subscript phi z given x, that gives us mu phi of x and sigma phi of x. And now the number of parameters is independent of the number of data points. So let's plug this into our math for the evidence lower bound and see what comes out. So this is called amortized variational inference. It's called amortized variational inference because now, in some sense, the parameter cost of variational inference is amortized via this second network. So this network is going to be trained on all of the data points instead of keeping separate parameters for every data point. So our goal, as always, is to bound log p of x, which, just like before, we can bound in terms of the expectation of the likelihood under Q plus the entropy of Q, except that now, instead of having Q subscript I, everywhere I have Q subscript phi of z given xi. It still depends on I because it's conditioned on xi, but now it's this neural network. So all I've done here is I just plugged in Q subscript phi in place of Q subscript I. And this is my new evidence lower bound. And just to be completely explicit, I'm going to explicitly write it out in terms as a function of p theta and q phi. So all the math stays exactly the same, all the stuff with entropies and KL divergences, but now I can actually derive a procedure for training this thing, for actually maximizing this evidence lower bound, where everything is trained with gradient ascent and there are no data point specific parameters. So what am I going to do? Well, for every xi, or for every mini batch, I'm going to calculate the gradient of the evidence lower bound with respect to theta. So to do it with respect to theta, first I sample a z from q subscript phi of z given x. So before I would sample it from qi of z, now I sample it by running my neural network, getting the mu and sigma and sampling. Then I'm going to approximate grad subscript theta of L using that sample, which again is just the gradient through this first term. I'm going to take a gradient ascent step. And then I'm going to somehow take a gradient ascent step on phi. And the trick here is, well, how do you calculate grad phi of L? That's the trick. We have to calculate grad phi of L. So to calculate grad phi of L, let's actually write out what L looks like, and let's collect the terms that depend on phi. Phi basically shows up in two places. It shows up as a distribution in the expectation, and it shows up in the entropy. Now, q subscript phi just outputs the parameters of a Gaussian. The entropy of a Gaussian is very easy to calculate. So you look up the formula, and you look it up in a textbook, or you look it up on Wikipedia, write it down, and then call dot gradients on it. So the entropy is very easy. We don't worry about the entropy. Let's look at the other term. The other term is the harder term. It's the expectation under q phi of some stuff. Now this is funny. The stuff doesn't depend on phi. The distribution depends on phi. Where have we seen that before? Where have we seen the maximization of a quantity, which is the expectation under some distribution, and you want to take the gradient with respect to the parameters of that distribution?
Importance sampling.
Importance sampling? Is there something a little more basic where we've seen this before? Let me write it out in a different way. Let me collect these terms, because they don't depend on phi, and call them R. So you have the expectation of R. Where have we seen that before? It's TRPO, yeah. So we saw it when we talked about policy gradients, right? This is exactly the same form as the objective and policy gradient. Replace Q with pi, and this is just the expected reward under a policy. So this first term, you can actually optimize it exactly the same way that you optimized policies with policy gradient. So you can go through the math for computing the gradient of this using the same likelihood ratio trick, and you will just get that the gradient, this should be grad j, that's a typo, grad j is approximately equal to the sum over some samples drawn from q phi of grad log q times r. So before policy gradient was grad log pi, now it's grad log q. So we can actually use all those tricks, the baselines, etc., that we learned about for policy gradient to do a better job of maximizing this quantity. And then we just tack on the gradient of the entropy, which can be computed analytically. So that's one way to do things, to just compute the policy gradient, or the reinforced gradient, and use it to climb the gradient for phi. What might be wrong with this gradient estimator? Does anyone have any thoughts about why this could be a little problematic? What were some of the issues that we learned about that policy gradient might suffer from? High variance, right. So the same kind of high variance issues that we saw with the policy gradient might give us some trouble here. And of course, the way that trouble manifests itself is that perhaps we use the policy gradient, we try to use that to improve phi, and because the gradient is high variance, the objective doesn't actually improve very much with respect to phi. Or maybe we need to sample many, many z's in order to get a sufficiently usable estimate of this gradient. So this gradient is still high variance for the very same reasons that the policy gradient was high variance. So I should say at this point that you can do this. You can use the policy gradient to maximize the evidence lower bound with respect to the parameters phi of q. And that will work if you do everything right and use baselines and all these tricks. However, in the case of amortized variational inference, there is a little bit of an additional tool that you have at your disposal, because unlike in policy gradient, here there is no notion of unknown dynamics. So everything here is known. Everything about q phi is at your disposal. You have all the parameters of q phi. They're all differentiable and so on. So there is another tool that you can use for amortized variational inference that was not available to us before when we talked about policy gradient. That tool is a little bit less universal than this type of gradient estimator, but it can work much, much better for the special case of continuous latent variable z. So, Right, because it's true for Gaussian z's, but it actually can be true for non-Gaussian distributions too. They just have to be continuous. So this is something called the reparameterization trick, and it works like this. So this is our objective, and our goal is to compute the gradient of this thing. The entropy term I omitted because the entropy term is easy. And our Q gives us the parameters for a Gaussian distribution. Now, let's think about this a little bit. If Z is distributed according to a Gaussian distribution, that means that you can write Z as a sum of two terms. Z is just equal to the mean of the Gaussian plus the standard deviation times some noise. And the noise just comes from a Gaussian with mean 0 and variance 1. So you can always transform a sample from a 0 mean unit variance Gaussian to whatever Gaussian you want just by adding the mean and then multiplying by the standard deviation. And the cool thing about this epsilon is that it is independent of phi, because it just has a mean of 0 and a variance of 1. So you can take this objective over here, which is an expectation under q phi, and you can rewrite it as an expectation with respect to epsilon. So you can write it as an expectation where epsilon is distributed according to a 0 mean unit variance Gaussian of the same reward r, except that now in place of z, we're going to substitute this equation. So now it's r of xi comma mu of xi plus epsilon sigma of xi. So now the parameters phi live inside the expectation, and the expectation is taken with respect to a random variable that does not depend on phi in any way. So this is called the reparameterization trick because we've reparameterized our distribution. Instead of having it be this thing which depends on phi, it's this thing which depends on nothing. And now we can compute the gradient. So how do we compute the gradient? Well, first we sample. We sample a bunch of epsilons from a 0 mean unit variance Gaussian. And then we plug the epsilon in here and just compute the gradient of this thing using our favorite automatic differentiation software. In fact, this gradient estimator has such low variance that just a single sample of epsilon is often sufficient to get usable gradients for gradient ascent. So even though here I have it written as epsilon 1 through epsilon m, in practice you would sample just one epsilon per data point. Plug it in here and run your favorite automatic differentiation software. Questions? Yes?
Why is the variance lower again? Like from one sample, from this straight.
Right, so the question is why is the variance lower? Well, the variance is lower because you can actually compute the gradient of this quantity analytically. Well, not analytically, but using automatic differentiation software. Back here, when we talked about using reinforce, grad r doesn't actually show up in this gradient estimator. So everything you learn about the gradient of r has to come from samples. Whereas over here, we're directly using the gradient of r. So the only randomness comes from epsilon.
But this is also sensitive to epsilon, like the choice of epsilon.
Well, epsilon has to come from a unit Gaussian. So there's no choice for epsilon. The epsilon has to be 0 mean unit variance. Here's a thought exercise. Let's say that sigma goes to 0, right? For sigma of 0, this gradient is exact. But if you go back here, for sigma of 0, this gradient is garbage. Because this gradient is going to have a 1 over sigma term, which is going to blow up to infinity. Okay, so the reparameterization trick is actually a very convenient thing if you can use it. Now, of course, you have to be able to reparameterize, which means that z has to be a continuous valued random variable. Basically, you have to be able to write this equation. You can't write that for all distributions and for all types of variables. Here's another way to look at this kind of evidence lower bound when we use the reparameterization trick. And this way of looking at it is going to be closer to what you would actually implement. So this is the form that you saw before. I'm going to modify this form a little bit. What I'm going to do is I'm going to just expand out the expectations. So I'll write this as expectation of the first term plus the expectation of the second term plus the entropy. And what I'm going to do next is I'm going to collect these, the second and third term, because these two terms together are just the negative KL divergence between q phi and the prior p of z. So KL divergence, remember, it's expectation under Q of the other distribution plus the entropy, and then the whole thing negative. So this is just KL divergence against the prior. Why do I want to collect these terms? Well, the reason I want to collect these terms is because P of Z usually has some very simple form like a Gaussian, and Q of Z given Xi also usually has some simple form like a Gaussian. So this KL divergence often can be expressed as some analytic equation. So if you have two things that are Gaussian, you look up the equation for their KL divergence in a textbook, and you can just write it down and compute its derivatives with automatic differentiation. So this term tends to be the easy term because there's usually a formula for it. This term tends to be the hard term because of the P subscript theta. And the first term is also the only one that depends on theta. So it's convenient when implementing this in practice to rewrite the objective in this form as the expectation under Q of log P theta Xi given Z minus the KL divergence between Q and the prior. And when you write it down like this, now you can use the reparameterization trick for the first term. So the first term just becomes the expectation with respect to epsilon of P theta Xi given mu of Xi plus epsilon sigma Xi. And the second term is the KL divergence. And then we'll approximate that first expectation by taking a sample of epsilon from the spherical Gaussian, so we can write that as being approximately equal to this thing where epsilon has been sampled from the Gaussian. But the KL divergence will calculate it exactly because it usually has a formula. So now we can visually draw what this computation graph looks like. You start with Xi, you feed it into your neural net parameterized by phi, and that gives you a mu of Xi and a sigma of Xi. Then you generate a random sample from a zero mean unit variance Gaussian. Then you sum these things together, so you take mu plus epsilon times sigma, and that gives you a sample of Z. Then you send Z through your other network, P subscript phi, or sorry, P subscript theta, and that gives you P subscript theta of Xi given Z. And now your objective function consists of two terms, the log of this for your data point, and the KL divergence over here, which you can calculate as an analytic function of mu and sigma. And then you just add those two objective terms together, call dot gradient on it, calculate a gradient, and then do gradient ascent. So that's how you would actually implement something like this in kind of a modern deep learning framework like PyTorch or TensorFlow or whatever. Yes, so that'll come on the next slide. This is exactly the form for the variational autoencoder, yes. Any other questions about this derivation? Okay. So let's kind of recap a little bit some of the pros and cons of using reparameterization trick versus the policy gradient style estimator. So the policy gradient, that's the one where you approximate grad J of phi as the average of grad log Q times R. This one has the big benefit that it can handle both discrete and continuous latent variables. So I've mostly been talking about continuous latent variables, but sometimes you might want discrete latent variables or a mixture of discrete and continuous. So this thing is very, very general. You can use it with any kind of latent variable that you want. But it has high variance. It might require multiple samples to be drawn to estimate the gradient accurately, and it might require smaller learning rates because of the high variance. The reparameterization trick, which is where you sample epsilon from some zero mean unit variance Gaussian and then calculate the gradient of your score function directly, that only works for continuous latent variables because you have to be able to reparameterize. You have to be able to rewrite Z as something of this form. But it's very simple to implement and generally has very low variance. So usually, if you can use the reparameterization trick, then you should use it. But in some situations, you might not be able to use it because you have, let's say, discrete latent variables. So those are the trade-offs between these two things. OK, so now let's talk about some actual models that we might like to train that make use of this idea. So the simplest model that we might want to train that uses this kind of amortized variational inference is something called the variational autoencoder. The variational autoencoder is a generative model, which means that it can be used to model your data, it can be used to generate samples of your data, and it gives you the density estimates for your data. And that's basically exactly what I described 2 slides ago. So the variational autoencoder is a deep neural network model that consists of 2 parts. It has a Q subscript phi, which gives you a distribution over latent variable z given x. So x might be, for example, an image, and z might be a vector of length 32. And for every one of those entries in that vector of length 32, Q gives you a mean and a variance. And then there's a second network, which is sometimes referred to as the decoder. So Q is sometimes called the encoder or the inference network, and P is sometimes referred to as the decoder. And P gives you a distribution over x given z. Depending on the type of data you have, P theta of x given z might be represented by a Gaussian, or if x is discrete, it might be represented as a categorical distribution using a softmax. So there, for P subscript theta x given z, you can do whatever you want. You can do Gaussians, softmax, a beta distribution, whatever you want. So the intuition behind the variational autoencoder is that you have some Gaussian latent space z, you sample from that space, get a z, use P theta of x given z to decode that into a data point x, and if x, for example, corresponds to images, you might get stuff like this. You might get samples from z corresponding to pictures, in this case, of people's faces. And when you see these faces changing, what this animation is showing is as you move around in the latent space, as you interpolate between 2 points in the latent space, the corresponding image changes, hopefully in some coherent way. So the variational autoencoder basically just directly implements this picture that I showed before. So the corresponding computation graph, it might look a little bit complicated, but it's basically just this encoder parameterized by phi and a decoder parameterized by theta. And there's a little bit of action going on in the bottleneck where you inject this noise epsilon to actually turn this into a proper probabilistic model. If it wasn't for the epsilon, this would just be a regular autoencoder. All right, and of course the way that you train the variational autoencoder is you maximize the log probability when you inject this noise minus the KL divergence between Q phi and the prior. So this first term looks a lot like an autoencoder because you have the encoder appearing here and then you have the decoder appearing out here. And this term just says the encoder should encode your observations into latent distributions that look similar to the prior. So this is the cartoon picture of how you sample from a variational autoencoder. You pick a z from the prior and then you decode. And the way that it works mathematically is you choose a z according to P of z, and then you choose your x according to P of x given z. Now, why does this work? Why does the sampling procedure work? Well, the somewhat unsatisfying textbook answer is that it works because you've just optimized the evidence lower bound, and the evidence lower bound is supposed to train this model, and this is the model, therefore you've trained it and it works. But there's also a little bit of intuition that, at least to me, makes a lot of sense. If you actually look at the form of the objective of the evidence lower bound, this second term says that Q should embed your observations xi into z into a distribution that is close to your prior. So if all of your training data was embedded into distributions that look similar to the prior, it makes a lot of sense that sampling from that prior will give you things that look like the data, because you put all of your data into the latent space in a way that looks like the prior. So if you generate new things that look like the prior, the corresponding x from P theta xi given z should look like your data. So, and in fact, if you remove this second term, then sampling from the prior will not work anymore. Okay, does anyone have any questions about the variational autoencoder? Yes, back there.
Is another interpretation of the loss function that you're encoding the total bits of information in the category, the model, and then the correction bits? So it's effectively trying to compress it and construct it as efficiently as possible.
Right. The question for those of you that are watching online was, well, does this objective, can it intuitively be interpreted as compressing the data or the model or something else? The answer is yes. This objective is compressing the data. It is not compressing the model. So the model parameters, theta, are not actually in any way part of the encoding. They're just sitting there. But you are compressing the data. And the intuition behind why you're compressing the data is that P of z essentially has no information about x in it. So if you're saying, let's make my code z corresponding to xi look like P of z, that amounts to saying, let's make my code have as little information in it as possible, because this KL divergence is minimized when z has 0 information about xi. But of course, you also have this first term, which forces you to keep at least some of the information. So you're trying to squeeze out as much of the information in xi as possible and put the minimum possible amount into z that is still sufficient to reconstruct. This interpretation as compression makes a lot more sense when we talk about conditional models, because for fully generative models, of course, there's only so much you can squeeze out. In the end, you still have to reconstruct all of x. But if you have some side information, then things become more interesting. So actually, on that topic, let's talk about conditional models a little bit more. So in the beginning of the lecture, I talked about how we have the simplest types of models, the P of x models, but then sometimes we also have these P of y given x models. It's actually very straightforward to get a conditional model using the evidence lower bound. So what kind of conditional model? Well, let's imagine a model of this type, right? You have some image that goes in, you're outputting some distribution over actions, and you want to feed in some noise and get this model to actually use the noise. So the variable that you're outputting out here is y. X now is just something you're conditioning on. So you're not generating x, you're just conditioning on x. So what I have written out here is the evidence lower bound for a conditional model that is generating y and condition on x. So now y always appears on the left side of the conditioning bar for p, right here, and x always appears on the right side of the conditioning bar. In fact, x appears on the right side of the conditioning bar everywhere. So it appears here, it appears here, it appears here, it appears here. So just like before, only now we're generating x, and everything is conditional on xi. And we can train this model exactly the same way that we did before. So the prior here in this illustration is just P of z. You can also make it P of z given x. That's up to you, whether you want a conditional prior or an unconditioned prior. So if we want to graphically illustrate what this model looks like, now you start with xi and yi. You feed both of them through your inference network, parameterized by phi. And that gives you mu phi as a function of xi yi and sigma phi as a function of xi yi. And these are now going to parameterize the distribution over z, which means that you're going to use the reparameterization trick, sample your epsilon from a zero mean unit variance Gaussian, and then you're going to calculate your z just like before as mu phi plus epsilon sigma phi. Now your decoder, your p phi, takes in both z and x, as you can see up here. So you're going to take x again, you're going to take your z, feed it through your decoder, and that'll give you p theta yi given xi comma z. So the only thing that really changed is that everywhere where we had x, now we have y, and everything is now conditioned on x. So we feed in both x and y, and here we feed in both x and z. And then we train in exactly the same way with respect to the evidence lower bound, and that'll give us a distribution over y, which depends on x, and which also use the latent variable z to represent very complex, potentially multimodal distributions. Any questions about conditional models? Okay. And then at test time, just like before, if we want to sample, we first sample a z from P of z, or if we have a conditional prior from P of z given xi, and then we sample y from our decoder, P of y given xi comma z. All right, let's talk about some examples of these kinds of models in practice. We saw a couple of examples already. So if you remember the advanced model-based RL lecture, we talked about this paper that had the embedding of the observations into a latent space where there was some funny stuff happening with cart poles swinging up and so on. Let me just restart this really quick so the video plays. Okay. There we go. So we saw this thing before, and to make it now a little more explicit, now that we've learned about variational autoencoders, the model in this paper actually consists of a type of variational autoencoder that also has dynamics in the latent space. So the latent space is not just Gaussian, it's actually a distribution over trajectories. And what this visualization is showing is actually the space Z. So this is actually visualizing the topology of Z. And when they show these So this is again the topology of Z here. Z is three-dimensional, and you see it's labeled Z0, Z1, and Z2. And then when they visualize their little animations, in the animation, what they're showing is on the left side is an original image, and on the right side is what happens if you encode that image into Z, add the noise, and then decode. So this is actually just the output from the decoder. So the general scheme that we discussed when we talked about advanced model-based RL was you collect data, you learn your embedding, and then you use some kind of control algorithm to reach the goal. But the process of learning that embedding, the process of learning this thing that I called G before, actually corresponds to amortized variational inference, where G is what I'm now calling Q phi, and the other edge, the solid colored edge, is P theta. We also looked at the result from this paper, which is using, again, an embedding of images to control a robot to stack some Lego blocks. And here, similar story. The model is a bit more complex, but it's also trained with amortized variational inference, where there is a type of variational autoencoder, this time that also models distributions over the dynamics. So you can actually sample dynamics based on trajectories and use those with, as local models, essentially, for model-based RL. And we'll see a lot more instances of generative models and variational inference in the coming weeks. First, we're going to talk about how variational inference can actually be used to provide a model of near optimal behavior, including near optimal human behavior, which can be used to compute objectives from demonstrations, and also new reinforcement learning algorithms. And then when we talk about exploration, we'll also see that generative models and variational inference can be used to formulate exploration objectives that get policies to seek out parts of the state space that are novel, that they haven't seen before. So next week we'll cover this stuff, and then the week after we'll cover the exploration. All right, so make sure that you get started on homework 3 really soon. Make sure that you accept the reviewer invitations for CMT, and see you all next week.